All right, let's get started. We want to welcome everyone back to the La Space Academy Level 1, Session 4 already. Can you believe that, Sherry? Session
No,
4, fast and furious, just like we like it.
I think we're in a time warp. It's seems to be moving faster every day. Maybe it's getting closer to the end of the semester, and we're all wishing that to happen. Maybe that's it.
Well, this is going to be a very fast and furious experience for you all, but it's going to be such a great learning experience. So not only do we have a great speaker tonight, but through the process of the La Space Academy, you're going to be learning very critical skills and practices and protocols that are going to get you ready to work at NASA, maybe with our next speaker, right? Or guest speaker.
Well, I think we have an ace in the hole tonight for you in terms of somebody who's a subject matter expert and going to be giving you a lot of great information. We will be posting, we have the PDR up, we're going to be posting the actual mission design and constraints document by the end of tonight, hopefully at the end of the session actually. And a lot of what Rick Davis, who's our speaker from NASA headquarters, is going to be talking about tonight is going to feed directly into what it is you're going to be tasked with doing. So we are going to do the big reveal tonight in terms of your project and the kinds of things you have to work with. And the cool thing about it is this is something that NASA's really going to need to have happen in not too near future. So we're hoping that this will give you some insight into looking and seeing how the humanity is going to move to the next place, not just in a satellite closest to us in terms of our moon, but actually to the next planet as we become a multi-planet species as we start to move out to those directions. So we did send out Rick's bio, is that correct?
Yes.
Yes, so everybody knows, and you have Rick's bio with you, a little bit about what he does. And I think we're gonna kind of tee this up and get Rick going. And Rick, why don't you say a few words, just again, a little bit of background, and then we'll kick off into uh, the amazing stuff you're going to be sharing tonight. So welcome and thanks for getting all the way back to DC in time for this. He was just in Arizona, so now he's back home and willing to jump on and talk to you all. Go ahead, Rick. You're muted. Just a second. So is Rick unmuted? Muted?
Yeah, Rick, on the very bottom left of your screen, you see the little arrow pointing up. There we go.
There we
We can
go.
hear you now.
Yeah, we're hearing you. Or maybe not.
We just lost it.
There, that's better.
We hear you
Maybe
now.
move the cord microphone up closer to your mouth.
Hang on. Let's try it.
Yeah, I think it was just tucked away in your shirt. That's kind of hard to hear.
Okay, is that any better?
It's a little
bit,
better, yeah.
Little light yet still on the amount.
I'm gonna take the mic off and see if that's any better. Hang on 1 second.
Way better.
Yeah.
Okay, how's that?
Much better.
Great.
Thank you.
Okay, so Sherry, how and Dan, how do y'all want to do that, or you want to get going, or what do you want to do?
Let's go ahead and just do a quick intro, like you did here when you were here. Just a little bit about some critical parts about your getting into the business, and then we'll launch right into your slide deck.
Mm-hmm. Okay, sounds great. So first of all, to everyone, thank you for the opportunity to come talk with you. I've been working Mars stuff for a number of years now, and I feel really lucky to do it. I will tell you that if I had one really strongly held belief is that Mars will be done, but it will not be done with just NASA doing it, nor will it be done with a bunch of big space agencies done. It's going to involve a lot of different players that maybe we probably haven't ever thought of in the past before. And I also think that you guys are really spring-loaded to contribute ideas, and we need those ideas. I'm going to try to give you an overview of some of those challenges as we get into this. And also, as you look towards getting out of school, I want to talk a little bit about some of the things that I think you can do to really increase your odds of getting involved. And as we go through this conversation, and I really stress it's a conversation, as much as this medium allows, and the chat log's really great, please ask us questions. I know Dan and Sherry are both hawking it, but I'm watching it too, because really we need to be talking about these things so that we can actually really come up with all the really cool ideas that we need. So thank you for tying in and being a part of all this. And again, please ask your questions as we go along. So a little bit on my background, because I would say that it's maybe a bit of a non-traditional background, but I think most people who end up doing things that they love doing follow non-traditional backgrounds. And I would encourage you not only just to realize that, but realize that finding your passion is really the key. And there'll be a bunch of false turns. I've had a bunch of them myself, and there've been some really amazing ones. And so I'll give you a little bit of a sense of that. I got a degree in history originally. I studied how frontiers impact societies for my thesis at the University of Virginia, and I fell in love with, I'd always been in love with the space stuff, but I really fell in love with it, with that work. And I decided I wanted to go back to school to actually get aerospace engineering. I actually went to school twice for 2 aerospace engineering degrees. But when I went back to school, I was really concerned because, you know, I'd already gone through school one time. I had student debt, all those kind of things. And I felt very fortunate that I met an amazing woman who had actually found out about a co-op program, or what they call it Pathways now, program at the Johnson Space Center, where she was literally training astronauts. And when I heard what she was doing, I totally fell in love with it. And then I applied, and I actually got in that program contingent on going back to school, because I try to make it clear enough in the application how much I wanted to do it. And I felt really lucky to get that. First, then I show up there, and they put me in software development, which is a little bit, for me at the time, a little bit like death. I mean, I was great people, but it was not what I wanted to do. And so the co-op director down there was amazing. And I just basically went to his office every morning when I knew he would be getting there before I'd go to work. And I say, his name's Jack. And I was like, Jack, I really want to be in crew training. And I will tell you, after about 8 days, Jack realized I was pretty determined to go do it eventually. And I told him every day I was there, I'd work hard as I could in software development. And he put me over there, and it was amazing. And my first student, I think, a real student, was a guy named John Young, who was one of the guys who walked to the moon, and one of the guys who was the first commander of the space shuttle. And, you know, when you walk into something like that and you're a college student, you go, what the heck am I going to do, right? But the point of the matter of fact is that he needed some refresher training, and that's what I had been trained to give him and before he went and did a simulation in the space shuttle. And, you know, I had to sort of gulp in my breath a little bit, but I did, and I got the job done, and it went fine. But the point being is that I had found I was, you know, was asking a bunch of dumb questions, and I was able to go do something I totally loved. And then, so I trained astronauts for a number of years. Eventually, I got sent over to Star City in Russia. I was there for almost 3.5 years, working because we were doing the Mir space station, where we were sending our crew members up there. And then we started doing the International Space Station training. And so we had to work with the Russians really closely. It was a really great time to be over there, because basically no one knew how to work it. And even on the US or Russian sides, on our side, they basically said, go make it work. And that's a great place to be if you like working in really fluid and dynamic situations. And if you all are interested in Mars, that's what we're doing. And so I did that for a number of years, and then I came back to the Johnson Space Center. I did international work for space stations. So I was working with the Japanese, the Russians, the Europeans, the Canadians. I mean, it was really an amazing group of people. And somewhere in there, I started doing flight control, and they actually, I had for space station operations, we had a shortage of astronauts who could be capsule communicators, or the people who, that's a strange name because we will have capsules again soon, but we didn't when the space shuttle was flying. But they were the people who were talking to the crews in space and representing the flight control team. And the Capcoms also are the cruise representative in the flight control room. And I really lucked out to get that spot. We had some, I forget, we didn't have a whole lot of us, but it was a great opportunity because I actually got to get a lot of the training that astronauts get. Went to Canada to learn how to use the arm and all that kind of stuff. And that's another one where just asking the question, can I do that job? I have to tell you, I sucked in my breath a little bit when I started poking around a little bit on that. And, sure enough, I think really just asking was key for getting the job. And I am really thankful because I did that for about 12 years. And I had some just wonderful experiences all the way from working a spacewalk, like 4 spacewalks where, you're the one talking to the people going out in the out in space, and that's another one of those moments in your life that when you experience it, will take your breath away. To actually helping co-lead a team that put the internet on board the space station, which I love. But no good deed goes unpunished, right? So I got sent up to NASA headquarters, and I worked in the office of our administrator, which is helping with policy and planning type stuff. I really fell in love with Mars stuff. And then I came back to the Johnson Space Center after a year and a half of doing that. And I really wanted to do Mars. And I'll talk a little bit about how I found those jobs because I was really knocking on a lot of doors. And I would encourage you all to knock on doors as well. And I'll explain that a little bit. And then I ended up getting a job where I am the co-lead for NASA's efforts to pick where we're going to set up a base on the planet, a permanent base. A totally cool process. And then I also lead or co-lead, whatever you want to call it, a bunch of other efforts that are really designed to help us figure out how to get to Mars and do that. And I'm doing all of that. I will tell you that there are tremendous opportunities for students to contribute, and we'll talk about those a little more as we get into here. And don't underestimate your ability to do really amazing things. We have interns that come work with us, for example, and I am always astounded at what they are able to do. And we'll talk a little bit about that as we get into it. So for this conversation today, what I want to do is I want to give you a sense of some of the cool challenges we're fighting with Mars. I'm going to focus on reconnaissance. Oh, so we have someone who's raising a hand, Sherry. Abram? Does that mean he's got a question?
If you have a question, go ahead and put it in the chat. Don't worry about raising your hand. That'd be great. Thanks.
Yeah, and we're all watching it, so we'll try to answer as many questions as we can. So I'm going to talk a little bit about some of the cool challenges that are out there for Mars. It's not intended to be an exhaustive list, but I really want you all to have some sense of that. And then we'll talk about reconnaissance and what we're doing on reconnaissance. I work in the Mars exploration program now, where it's traditionally been science, but we are really trying to look at reconnaissance, which is different. It's the information we need to have to be able to send humans to Mars to land on it and actually be very successul. And so I'm going to try to give you, that's what we'll focus on. And there are a few questions that I'll try to answer them here if we can. So I have worked with Jason Cruzan. Christopher asked that. He's a very creative guy. And let's see, he counts the astronauts on ISS. So that's a great question. I will talk a little bit about that and then we'll pick back up. But when you are a capsule communicator in the Mission Control Center, I would say a couple things. One, you are responsible for understanding what the flight control team is trying to tell the crew and telling them that. But you're also responsible for being in the heads of the crew members and representing their perspective. So a lot of times an engineer will get too technical or too detailed and they're not putting it in terms that someone doesn't know that system well. And so your job is to translate it a little bit. And the other thing you're doing is you are really trying to understand where the crew's head is on this stuff. And we've really had to learn how to do that in space station operations. So to give you an example, these people are locked up in a can in space for 6 months at a time. And so they get fatigued and that kind of thing. And so one of the things you're expected to do is sort of understand how much work they've been doing the days before, understand how they work best, and then represent that in the flight control team as one of their advocates for making sure that we don't overwork them or overdo them. And I'll tell you some funny stories about that as we get into this a little bit. Okay, so Sherry, if you want to cherry pick some of those questions as we go along, we'll go from there. But we'll start with the pitch.
Yeah, I'll ping you when there's something that comes up that we should answer right
great.
now.
And we got a fair amount of time, and we'll try to get as many of these as we can, everyone, because the questions I've seen are fantastic. So this is looking ahead to human exploration of Mars, or really a reconnaissance, but really I love the title. And I love this picture right here because we made this picture about within the last year, and it is where a hillside at Mars has slid away. We used to think that there was no water on Mars. And what you're seeing here literally is a pure water ice that has been revealed because the hill slid away. And it is, to give you a sense of scale, you could stack up multiple Eiffel Towers in here, and it is that thick of pure water ice. And that is really transforming in terms of how we go do exploration at Mars. Because basically, on this planet, we don't go anywhere if there isn't water, or we don't stay there for long. We are water creatures, and we need water. And so a lot of what you're going to hear me talk about today is what we're doing to find the water, make sure we can use it at Mars, because it is completely enabling for having humans live and operate and be extremely successful on Mars. And there's a great question from Nathan right there, which is, where is this located? There are actually a number of locations like this. I think it's like 5 or 6 is the approximate number, but one's in the northern hemisphere, and the rest of them are down in the southern hemisphere, and they're all over. And we're just beginning to figure out how to look for these things. And so that's really key. Okay, let's go to the next slide. Okay, so before we get going really far, I want to talk about the real Mars. Because when we do really think about it as it is, it makes sure that we don't screw things up. So a lot of this in the upper left-hand corner is a panorama that was actually done from Gale Crater on Mars. I think it was like in the last year and a half or so. It is beautiful. I love this picture right here. But a lot of people, we have paradigms, and we'd use paradigms to help organize our thinking. A lot of people will automatically go down and think, oh, it's like a desert on the earth, or like this one in Jordan. And there are pictures in some of these deserts where they look almost identical. And that is extremely misleading, because the real Mars is more like scaling up K2, which is down in the lower right-hand corner, where you are going up this extremely dangerous thing. And it's, and it could even be frozen dead bodies along the way. And it's not that we can't do it, it's just that our technology is just now evolving to the point where we can go up K2 and actually do it fairly reliably, because we've learned how to do it. We are going to do the same thing at Mars, and I fully expect there could be some of the people online here right now that will be going up out onto this beautiful crater of Mars at some point. But you got to realize that it's dangerous, and then earn your way and make sure that that perspective is in everything you do, so that you do it the right way and don't end up killing somebody. And so, not to say you don't do it, but you got to have the right perspective there. So anyway, any questions on this slide, Sherry?
Yeah, actually somebody was saying, so we have to go and locate water. We got that 100 metric tons of water constraint. Can you do synthetic water creation? Is that something that's even thought of, or is it even possible, or they have to invent it?
You can make water, but you don't really need to. And we'll talk about this a little bit. And Mars has actually, it used to look like Earth, and it has buried oceans. It's buried glaciers. In fact, if you I don't know how many billions of years ago, but if you had looked at it, it would have looked like our home planet here, in all probability. Things happened to it that actually caused it to lose a lot of its atmosphere, and then to get very cold, and then the water all froze, and then it gets covered over time. But we know it's there. We actually have, there's a number of reasons we know it's there. For example, we have radars that we've flown and we'll talk about this a little bit more, but that we can actually see the water, measure it, and see to a large extent how thick it is. So the really cool thing is that when meteors come screaming into the Martian atmosphere like they do on Earth, right? On Earth, though, there's a big atmosphere that actually causes most of those to be burnt up. On Mars, there is an atmosphere, but a lot of them get down to the surface. And what we can actually do is when they go screaming and crashing into the ground, it actually strips away the dirt. And in some of these places, we can actually see pure white ice and actually detect it. And so that's a visual cue that there's actually pure white ice. On the Phoenix mission, it went a little further north, and we actually had a scoop on it where we scooped it up and saw pure white ice. Now the atmosphere is very thin, so when you do a scoop there or the meteor crashes in, it actually will sublimate and disappear over time, and then all you see is dirt from there. But there is actually pure water ice in large quantities on the planet, and that's extremely exciting. Anything else? Sure.
No, I think we can go ahead and keep going for now.
Okay, let's go to the next slide then. So keep going. So this slide I love to do just to give you a little sense of the challenges we have at Mars. And I'm not going to cover all of these, but I will hit on a few of these key challenges that we see out there. And one is that the mothership that goes from Earth to Mars, it's basically cycling between the two planets. And that when we send people out to Mars, I really want to ask everybody one quick question to see what kind of answers we get. Can anyone tell me how long a mission to Mars is from when they do the burn? I'd love to see where people are. Let's see, 2 years, 6, 7. Oh, cool, great answer. A lot of these. Okay, great. Well, we have several people with the right answer, which is it's a 3-year mission, roughly 1,100 days. And what's really amazing about it is when we sent people to the moon, the moon is locked around the Earth, and so those missions were set up so that even if you couldn't land, you were going to sweep around it and come back to the Earth. When you go to Mars, when you light those engines, you are gone for 3 years, just because of the way it takes for the planets to line up and the way the trajectories work, and you are not coming home. And that is a really fascinating challenge. It's not an unheard of challenge. And what I mean by that is in the past, like the Lewis and Clark expedition, I think they were roughly out almost 3 years. When Amundsen and those guys went down to the South Pole for the first time, that was also a similar period of time from the time they actually left to the time they actually got back home. So they were gone a very long time. Human beings have done this, but it is a long time. And so when I think about this ship that takes them all the way out to Mars, it is really, you've got to make sure that they have everything they need, whether it be food, water, science equipment, because the one thing we've learned is that when you put people in that kind of dangerous environment, you want to make sure they are productive and doing meaningful things. And if we have not done that collectively, then we have not, we are not only missing a massive opportunity, but we're actually putting them at risk, because that one of the key ways to keep a crew member happy on a very challenging, risky mission is to have meaningful, productive work. Another thing that you have to do in that kind of a thing, and we've learned this because when we first started working with the Russians, they'd kind of laugh at us sometimes because we'd only done short shuttle missions, and they'd been doing long duration missions for a long time. But you have to really think about what people need. And so one of the things I like to talk about is that, like, y'all are all in school, and when you get off when you're finished with schoolwork for the day, we all have to kind of chill a bit and actually watch TV or game or do some gaming or whatever to kind of or listen to music. And those things, a lot of people think those are optional, but I don't think of those as optional at all. And I think in reality, all of us would admit that they're a key part for handling a very stressful workday. When you are in space, it's the exact same thing. And so one of the things this vehicle has to do is it also has to provide the ability to store TV shows, music, and all those good food, and so that we can make sure that when we work them hard each day for 3 years on end, where they can't be with their families, that they have downtime as well. So that's a key piece here. And so, on the space station, if we had a rule, the more we can make it feel like home, the happier they were. And that's not a warm, squishy thing. You want them happy also so that they can handle the stress loads of being in a very hostile environment. I will give you a silly example, Sherry. You've heard this one, but we had a crew in the early days of space station where we were not really aware of those things as much as we should be. I don't know about you guys, but some days if I've had a really crappy day, and I'm pretty good about what I eat, but I will tell you that sometimes I gotta have this amazing fudge ice cream, and and we're all like that. Food's a big deal. And so on the space station, we had one set of crews they've been working very hard, and they were slamming through the dessert. And so they slammed through them so much that the next crew came up and they had an even harder set of mission. And we were very short of desserts. And in fact, it became such a stressor that we actually had any email about dessert or food of any kind actually had to go through like 5 levels of management. And I am not kidding you about this, before it went up there to make sure that it was all coordinated what we were saying, because they had been so frustrated by that lack of planning. And it's not on them. It was on us for not thinking about that. And they worked around as best they can. And then that's a negative example. Here's a really positive example. When the Russians send with their supply ships, which are called progress vehicles, up to a space station, they will put fruit right on top of all the supplies. So when you open the hat, you get this whiff of amazing fresh fruit. Now, for me, I don't like fruit, so it would not be amazing, but for most people, it is amazing. And so that, I cannot tell you how many times I have been on console and heard crew members talk about how wonderful that is. And so when we envision these vehicles that go out to Mars, they need to be able to, to support those kind of things and make it feel as much like home as possible. I would say 2 other things about that vehicle, and then I'll try to go into the other 2 points on this page again. Number 1 is that our sense of space, how much space we need in spacecraft, has been changing. And so, we all take space for granted. We can walk outside, we can go to, we can go for hikes, we can do other things. When you're in a spacecraft, you can't do any of those things. You might be able to go out for a spacewalk, and that would be totally awesome. But the fact of the matter is, we can't even do that often. It's so dangerous. So the space you have is there. So when we start, if you look at a Soyuz or a space shuttle, it was pretty cramped. And then when we jumped to space station, we learned we needed a lot more cubic meters per crew member there. Now on the space station, if you need to, you can get home, and you are looking at this amazing home we have that's like just designed to create life. When we do that engine burn to send them to Mars, and they know in their heart and soul that they can't come home for 3 years at that point. That is a really transforming moment. And as the Earth recedes in your view and becomes just a tiny, tiny blue dot in the deepness of black space, I don't think we can really understand how much space a human needs in that kind of setting, nor do we really even understand totally yet how many crew members we need to have to make sure there's a good social dynamic there. And so we need lots of ideas on that. And there's a lot of work going on all those fronts. Let's take a little break and see if anyone's got any questions there. Sure, do we?
I'm thinking that there's just a lot of conversations going on in terms of the kinds of things you'll need to get to Mars and how big a rocket and those and the muscle loss also, Rick. I know you talked about that previously one other time that we were talking.
Yeah, I was just getting that. And so so another key piece is that is exercise, because when we are walking around all day, we also don't realize that there is a lot of exercise that we're getting just being in a gravity field. And when you're in zero gravity, you don't get that exercise. And so we require that cruise members actually exercise about 2.5 hours a day. And so half of that is roughly spent on cardiovascular training. The other half is spent on anaerobic exercise. So the equivalent of weights, but weights don't work in space, right? So we have to have essentially like, I forget what they call them here, but they're basically rubber band type systems that have loadings on them and that we measure it. And the equipment is incredible for doing that stuff. But that is a big piece to do it. And what's really fascinating about Mars is when they'll have gone to get to Mars takes about 6 to 9 months, and then it takes another 6 to 9 months to come back. But then you have to wait for the planets to line up after you get to Mars, and so to give you that total mission length of 1,100 days. And so when they get ready to land on Mars, they haven't had any. They will have gone through a very strict exercise protocol. But when people land on this planet after having been on the space station, we have doctors there to help them. They pull them out of the capsules and then have them feel faint, or they're really weak or disoriented. And I think when they get to Mars, they're basically on our next planet without anybody there to help them. And we have to learn how to do all that. And we may even have to increase how much exercise they get and have to come up with all kinds of creative ways to do that to really make sure that we have a really good answer so that they are ready to handle the job of really working on an alien planet. Okay, so I want to touch on two things. The other thing on this list was about 5 bullets down there. Walking out in space is totally cool. Walking on an alien planet is going to be as cool, if not cooler. And so I will tell you, there's a lot of really amazing work that needs to be done on that. So we are really good at building spacesuits now, and in fact, we don't really call suits on the moon or Mars. We keep calling them spacesuits, and in point of fact, they're surface suits. But at the Mars, we got to make sure these suits. I'll just give you one example of the challenges on the moon during Apollo 17. The moon's dirt, or regolith as it's called, we never had weathering. And so the challenge there is that it's like glass shards. And on Apollo 17, if they'd gone out for one more moonwalk, they actually those glass shards would have cut into the suit so badly that they would have actually probably experienced a depressurization, which basically can kill you. And I'll never forget talking about this in the audience, and then I realized that Jack Schmitt, who actually was on that moonwalk, was there, and all he could do is nod his head up and down. And if I ever had a doubt about how serious it was, that afternoon told me how serious it was. But it was serious. Now at Mars, Mars had weather. It was like the Earth, like I said, but it is somewhere between the moon and the Earth. But we got to make sure those suits can handle abrasive regolith, and that's just one of the challenges for building a suit. So that if you guys, and it'll be you guys, are walking on Mars, you can do so safely. And there are a lot of other cool challenges just in that one area. Now today, I am really trying to focus on the last bullet, which is what do we got to know before we actually send people to Mars, or even attempt to do it so that we can do it well. And that's what the next slide's trying to address, if we can go to that. And there are a few questions there, sure. Maybe we can try to take one or two.
Well, I'm just kind of monitoring them. They were asking about dust storms, Rick. In terms of the kind of planning that you're doing for the human landing sites, has that been raised in terms of, especially since we just got done with the global web, dust storm at Mars that took out, possibly we have not been able to hear back from the Opportunity rover because of that. Right. We're still waiting to see if that ever wakes up. But what are we going to do with humans?
So we're going to talk a little more about weather in general, but I love that question. And so dust storms are very challenging because it's not like a storm on this planet. Some of these dust storms can actually envelop the entire planet. And when they do, the real hazard is there's a number of problems. One of which is that they can cut out the sunlight, so that if your base is dependent on solar arrays, which the Opportunity rover was, then you essentially can get to a point where you can't generate any power. And that's actually, we're still trying to recover opportunity, but it's been a while, and we may have lost it. But the point is, it needed, it had solar arrays. That was its primary power. When it couldn't get it, it went on to batteries and it shut itself down. So it wasn't, and this is the plan. It was so that it was trying to extend how long the batteries could go. But, it went so long. I mean, it started like in April, May, I think, and it was basically almost a full 6 months, as someone on here said. So that's just one type of weather we really need to know. And I'm going to talk a little bit more about what we need to know about weather, because there's a lot of key things we need that we can't do yet. And what I call small missions are a key piece, I believe, of helping us understand these kinds of challenges. And you'll see that in a moment. Let's see. Okay, so the human landing site study. It's one of those things that I was lucky enough to get asked to co-lead this thing, and I say lucky because not only is the work totally fun and cool, but the people that I get to work with are some of the most forward-looking, open-minded people I've ever had the pleasure of working with. Sherry was at that workshop, and she's right in that crowd, and she can tell you too how great the whole team is. But I just feel lucky to work with them. And we wanted to get going on this problem because where you set up a base, and I actually tied in a little early, and I could see where they have a whole team looking on that particular, or sub-team on that particular team, they're looking at base selection. And that's really important, because that your base location, you got to make sure there's resources there, and we'll talk a little more about that. You got to make sure there's cool science to do there. And we had never really looked at that on Mars very extensively. We're starting now, because what we're learning is that there is a ton to learn, and you have to, and the homework you have to do takes a long time sometimes, and it's largely driven by the fact that to get out from we only get a chance, a window to go to Mars every 26 months, and then you got to plan it, you got to get in there, and then you can send it out in one of these launch windows. And then when you learn something, then you may have to change or have new spacecraft that go out there, and that seriality really creates some challenges to get all the information we need to have. So we wanted to get going on it so we could understand it, start identifying sites. We actually identified 47 sites, and this map below, Sherry's probably shared it with you guys, but that is actually the little circles are proposals from there. Our first workshop was totally open, and it was the coolest thing because we had people from all over this planet proposing sites where humans are going to live eventually on our second planet. And that's what you're seeing there. And we had people from the Ukraine, from France, from all over tied in and helping us try to figure out what we need. We then actually started we offered up for high priority data needs. We actually agreed to turn on cameras and sensors at Mars. So to support this effort, we've actually been imaging sites to better understand some of these challenges. And so it's interesting. SpaceX was using this data that we've been collecting, for example, and when they were going to send their Red Dragons, they were aiming for Deuteronomus Mensae, which is up in the upper portion of the map in the center. And because of those data collections, we actually realized that the surface was tough. It had too many. It was essentially impossible to land a spacecraft on there safely. And so they had shifted where they were aiming as a result of that. And that's an iterative process. But that is already informed us. In fact, we have Google Hangouts where you can hear. We're actually starting to have people who these site proposers request data debrief or tell us what they're learning, so that other people can start factoring that in terms of their next proposals, which is really pretty cool. And the thinking is amazing. Y'all actually might enjoy doing that. The other thing which we wanted to do is start figuring out what it is that we need to do next to better understand what's really needed. And out of this workshop, which is at the end of 2015, the big thing was knowing more about water. And that implies orbital and landed missions. And we're going to talk a little bit about that. Any questions, Sherry, that we can try to answer?
I think we're good.
Okay, so if we go to the next page. Okay, I'm not going to spend a lot of time on this page other than just make a few points. This is the current and soon-to-be fleet at Mars. It is an amazing thing that we have sent this many things to Mars. And when I say we, it's not just NASA. If you'll look there, there are international missions that are out there, such as the Trace Gas Orbiter, which is ESA, and the Russian space agencies. The Indian Space Agency has the MOM orbiter, which is there, and it is really and truly an international thing. As someone who, as someone who grew up, as a United States citizen, I'm incredibly proud that the United States is the only country that has actually mastered successfully landing on Mars to date. But I will tell you, from NASA's perspective, we are working very hard with our international partners to make sure they have the full advantage of that information so that they also can be successful. It is hard. The atmosphere is basically thick enough that you can't ignore it, but it's thin enough that you can't really use it to slow you up that much. And so on landing site constraints, one of the things you'll see is we actually have a minimum altitude that you have to be in. The whole game there is we're trying to keep it as low as possible so that we can ensure there's enough air to help slow the lander when it's coming in there. And Austin just mentioned the Sky Crane. And the Sky Crane, it was a great thing. You ought to talk, I would love for you guys to meet the guys who actually invented that. They are like radical.
Yeah, they are.
But the thing about the Sky Crane was that we didn't, there were a number of reasons that drove us into it. And so that technology is just incredible. One of which is that when you land on these things, if you look at the Sky Crane, what it's actually doing is it's got the jets and they're canted away so that you're not blasting the dirt up, and because there's no landing pad there, right? This is just dirt. And so they were trying to make sure it was pretty pristine there, and then they come that cable and drop, in this case, Curiosity, but we have a new rover that's going in 2020. It's going to use the same technology with some improvement there, and it was pretty creative. But it takes that kind of creativity to do this stuff. The other thing I would say here is look at these other participants that are starting to come in there. So you've got at the United Arab Emirates going in there. You got China aiming for Mars. I mean, this is really a worldwide effort in terms of opening up this frontier. United Arab Emirates, totally rocks. They are using this as a way of giving their students really cool opportunities and to encourage something that's really transforming for their society. Because if you go into their space center, which I've had the good luck of doing, 40% of their engineers and scientists are women. That is totally amazing accomplishment for them, and you don't see that in their normal day society. They are totally using this frontier to help achieve a major cultural goal for them. And it's really pretty cool. Okay, I think that's all I wanted to say on this. But the point is, we also have all these assets, and we're trying to use them to help answer these questions about Mars in terms of getting ready for humans.
Hey, Rick.
Yep.
So Mariah wants to know that some of the most interesting places are under planetary protection. How does that interfere with site selection for a long-term base? And how would you prevent contamination?
So that's a great question. That was Mariah who asked that, right?
Yeah. Yep.
Yeah, great question, Mariah. So planetary protection is for every, just to make real quick, I'll give you the farm boys version of that. Essentially it's trying two goals. One is to make sure that, one of the cool reasons you go to Mars is to look for whether or not life evolved on another planet. That has massive philosophical as well as science ramifications. And so, but unfortunately, humans and our biology on this planet just oozes everywhere. We by mass are like 50% by microbes, or maybe it's actually a little higher. And so when we go to a place, we don't want to goon up the cool science we're trying to do, and so we're trying to make sure that it stays relatively clean. The other concern is that if there is a biology on Mars, we have to make sure that if it's hostile, we're going to make sure we don't bring it back to this Earth and create a big problem. called backward contamination. And so in terms of the forward contamination, making sure you don't mess up the science, we actually kind of know how to do that already because we do that in Antarctica. We know where the bases are, we know where the prevailing winds are, and then we maintain pristine areas for doing essentially astrobiology-like work there. And there's really amazing work that is probably very similar to what we have to go do at Mars, because in Antarctica, we find life in rocks, we find it in the subsurface. It's at Mars, it'll probably be, if it's there, it'll probably be very similar. And I would actually, we have to learn to manage that risk. But I would even say that when human beings go, I am hoping we have astrobiologists going along on those initial crews, because my suspicion is that it will be so hard to recognize an alien life that you might actually need humans, and in particular biologists there, who understand what that means, and they can say, ooh, that's really different. So Jack Schmitt on Apollo 17, to give you an example, he was the first scientist, the only scientist so far that's going to the moon. And his ability to look at rock formations, because he was a geologist, and find really cool and amazing things, was significantly higher than anybody else who wasn't trained in that way. And we're going to need the same thing from a biologist standpoint, I believe, when we get to Mars. Okay, so great question. Thank you. So the workshop we had, and it really increased that the whole goal of Mars is a big thing, is that base selection is largely driven by water. I'm going to talk a little bit about some of the main uses of water. I'm sure Sherry and Dan and the whole have already talked about those, but I want to stress a few of them, maybe from a ops guy's perspective. And so the interesting thing is we realized that there were a lot of gaps in our knowledge of where the water is. And I'm going to try to give you a sense of that. But then there are also gaps in our knowledge of the production technologies that take to work on Mars. And so we'll talk a little bit about those challenges too. And then the next thing is, for years, we thought it was like a dry, dead planet. We had no clue that it had so much water on it. And really the discovery of these ice fields was really in the last 10 to 15 years. And so that we are also reassessing how we do our architecture, because with that water, I think there's some really exciting opportunities. Any other questions on this page that we can try to answer?
I think we're good. There's some conversations going on about terraforming. I just put an article up in terms of what NASA released from Goddard just not very long ago.
So but I actually love those questions. I saw a few of those, and I love those questions. So I would make this statement. We are already terraforming on this planet. If you go to Los Angeles, and anyone here from Los Angeles online? Let's see if anyone is.
There's a few hands.
Very great. Yeah, lots of yeses. Very cool. So when you channel rivers like we're doing in LA, or when you have like these massive road systems and it's tons of concrete, Merry Christmas, that is terraforming. It is a localized version, but the human species is becoming so extensive that we are impacting this planet. And we have to start learning how to, we don't call it terraforming because we don't really think of, sort of the word even applies, make it like Earth, but we are essentially emerging to do planetary level scale engineering. And that will occur at Mars as well. And it'll be local at first, but then it'll actually become much more extensive. And I just think that's just inherent to what an evolving, growing technology is done. In fact, may be crucial for taking care of this planet. So it's a very cool question. If we go to the next slide, good. Kelly has a question, I think, maybe.
I'm looking.
And don't raise your hand. Just ask the question in the chat log, and we'll try to keep up with it.
We'll do that.
A lot of great questions. Well, let me talk a little bit more, and then we'll see if we answer them, and then we'll get through there, okay? So Mars has two great types of water there. The first one is the subsurface ice, and what you're seeing right here on the left-hand side of this slide is what we call sheet ice. It's actually probably buried oceans, and they're very extensive things with radars. We can largely see, we can see where the tops are and where the bottoms are. And we're talking, basically these are oceans. The other one is there are glaciers, which tend, the landscape tends to be rougher there, but they definitely have ice, water ice there, and in large quantities. And so that escarpment that we showed you would be an example probably of a glacier area that where it actually has collapsed dirt, and you see that pure ice there, which is really exciting in terms of resource. Our challenge in terms of reconnaissance for subsurface ice is when we sent the radars out to Mars, we were looking for deep liquid water aquifers. And so we chose frequencies on the radars that only could see deep and try to find that what we thought was liquid water. Now, on any frontier, you always end up with what makes them cool, right? You find out things that you never even thought about, and we weren't looking for ice. But the challenge is that the frequencies we chose essentially gave us a blind spot between 0 and 10 meters where we can't see it. And if you go to someone who's actually trying to produce water through or local use of water on Mars, or we call that in situ resource utilization, horrible name, but that's what we call it, ISRU. When an ISRU person would really want to be in that 0 to 10 meters. This means you're not drilling through unknown overburden, and it's a much simpler problem if it's not really deep. And so we really need to close that gap and understand what it takes to do that. The good news on the technology front, we've got a lot of work to do there too, because no one's ever extracted water from a buried ice on Mars, and there's very low pressure, it's extremely cold, the machines that need to work, we need to get the mass, the power, and the operational complexity of those equipment down. Now the good news is that in Antarctica, they actually do have what we call rod wells that are where you essentially drill down, you put a heat source, you melt the ice, pull it up as liquid water, and they pull it and they use that to supply water to lots of people. So we actually have a prototype of this on this planet that is used daily. And we actually just turned on a contract with the National Science Foundation guys. It's an outfit called CREL to go start building up models of what it would take to do the exact same thing on Mars with Martian conditions, like the pressure and the temperatures and that kind of thing. So we're starting work on there. The other type of water source, which is more prevalent around the planet, is hydrated minerals. Let me talk a little about subsurface ice. Subsurface ice is largely in the mid to northern latitudes. And that is also a challenge because it is colder up there, just like it is on this planet. It gets colder in the winter. They have pretty severe, they have winters. And so it's colder, machines don't like working. And I'm not talking, 32 degrees Fahrenheit. I'm talking, something like 70 degrees below zero, right? It's cold and colder at night. And so those machines, we have to think about that. Well, and then because it's dark in those areas, like it is on our planet in the wintertime, you can't produce electricity with solar arrays. And the last challenge that we have to understand is that when your ride home, we call that a Mars Ascent Vehicle, or MAV. I love that term. But the MAVs, when you launch off a planet, it really helps to be down near the equator. That's why we have launch sites at Cape Canaveral and French Guiana, and anyone who's trying to do it, they often try to be down at the equator because the spin of the planet helps you with your launch and makes it and saves a lot of propellant. When you go up further north, that doesn't help you so much, and so that it could potentially impact our ability to come home. Now, hydrated minerals are another type of water thing. That's basically dirt, if you will, or really called regolith, but I'm going to keep calling it dirt. That's what we all know. But it's dirt that has water molecules locked up in it. That could either be rocks with water molecules or that. And you can bake those things and actually free up water molecules that way. The challenge is that I'm going to talk about the recon challenge, and I'm going to talk about the tech development challenge. The recon challenge is that our only ability to see that is with spectrometers from orbit. And the challenge there is that you can't get depth, and you can't, and the resolution on those spectrometers is such that you can't tell whether or not it's a little vein that's causing it to trigger, or whether it's a field that's doing that. And so we could think we're seeing it there, and then also we get down the ground. And we have done this. We've actually sent Curiosity looking for something, but we can't find them because something's triggering that signature in space, but because it could be a vein or it could be a field, and we can't find it. And so it just understanding that and really proving that it's there with just orbital information is challenging. And then not only that, spectrometers only look at the skin of the surface. They don't go deep. And so we don't know the density, and we don't really know how much is there. And that is probably a very difficult thing. And on the production side, doing it efficiently with minimum energy is a concern. The fact of the matter is that on this planet, we do not scoop up dirt and bake out water anywhere that I am aware of. And it's because it's energy intensive, and it's also operationally challenging too. And so with all of these two types of feedstocks, in terms on the production side, we basically have to answer the question, what is the mass of the equipment that it takes to get it there? What is the power levels that it takes? And the third question is it operationally complex to get it? Because when you are in a dangerous environment like this, you do not want to have extremely complicated operations. That is a surefire way to kill somebody, and we want to be careful about that. Any questions?
So, yeah, I have one and we're talking about the difference between going after the water feedstocks that are ice versus hydrated minerals. And so Christopher was asking, are they going to use conventional microwave sintering? Basically, are they going to bake off the water out of the hydrated minerals, if that's the way you're going to go? And I think you have some evolved thinking about that in terms of where you're going with the landing sites in terms of choice between hydrated minerals and ice. Is that right?
Yes. There's So and there was a question by Kevin too, which I wanted to try to get to.
I'll find it. Go ahead.
But for this question, I actually think that where we are today, if I had to bet money, I would bet that we will probably go to subsurface ice. We have a mapping effort underway to build next generation maps. We're seeing those lines coming down to 35 degrees north, and we may be able to find other spots in even further south. I'm reasonably optimistic we'll be able to do that, and it's pretty low energy, and with what we're learning from Antarctica, it's a pretty efficient way of doing it. But on frontiers like this, you want options for bad days, and my suspicion is that we will want we'll be using the subsurface ice, but we probably won't have an insurance policy of having a really good hydrated mineral field nearby so that we can extract that if the other one doesn't work. Human beings need water, and we got to make sure we have a robust supply for it.
Well, I'm seeing a whole bunch of Kenneths in the chat.
It was Kevin, actually.
Oh, Kevin. Okay. I was going after Kevin. So I don't know if you remember what the question was or not, Rick.
God, it was, I wanted to answer, but then you asked me the other one, I got lost. So Kevin, if you can ask it again, please.
Yeah. Okay, Kevin. The real Kevin, step up into the chat. Or the multiple Kevins, we'll see.
Okay. Let's go to the next slide, please.
Oh, okay. I got the question for you.
Okay.
Can we only find liquid water under the surface because it needs pressure not to sublimate? So is there like underground aquifers, you think, on Mars, Rick, that we're going to tap into, or are we just looking basically for ice layers?
So we originally thought there would be, but I think as a result of the work that's been done with 2 different radars that we're looking for, we pretty much know that there is not readily accessible liquid aquifers in any reasonable depth on the planet right now.
Well,
and let me finish.
Go ahead.
There was one team that has seen evidence of some sort of liquid lake potentially, but it needs to be vetted. But it is underneath one of the poles, and frankly, you do not want to be operating up there. It is extremely cold. Carbon dioxide, which snows, and if you look at the point that it takes to make carbon dioxide snow, it is miserably cold, and the machines just will not do very well in that kind of environment. So So I think the community is largely moving towards, heading for ice is my belief. With
Well,
probably, yeah,
go
go
ahead.
ahead.
I
No,
was
go
going
ahead.
to say, even at the equator, equatorial regions, that they have to plan on the rovers being able to operate in the diurnal cycle from day to night at
Right.
a 100 degrees difference. So it gets like 100 degrees below zero basically at nighttime, because the atmosphere is so thin, which some of you have been talking about, 1/100th the amount of Earth in terms of the atmosphere there. There's no good blanket of air like Earth to keep any kind of heat in. So it radiates straight out to heat, and the sun goes down on Mars, and it gets very cold. So
Yeah.
that's even equatorial. You can imagine what it's like at the poles.
So Sherry, how are we doing on time? I just want to make sure we
We
have
got a
time.
half an hour.
Okay. So let me talk a little bit about this slide, and we'll see if we can try to answer a few more questions. So what are we using all this water for? And frankly, I'm not sure where you all with the class, but it actually surprised me. And when I came to doing Mars, the big reason we are using water has nothing to do with the normal uses of water. It is actually to provide propellant for that Mars ascent vehicle so that it can get off the planet and come home and get you up to the mothership or the Mars transfer vehicle and bring you home. And so the simple fact of the matter is that it costs so much to actually bring anything from Earth all the way out to Mars that really we would take this risk of actually using local resources to fuel up the Mars ascent vehicle. And so it's a two-step process, actually, because in the initial missions, the large amount of mass, the biggest amount of mass is the oxidizer, which is oxygen. And I firmly believe that we will just crack the carbon dioxide atmosphere initially and then produce the oxygen with that. We'll probably bring the methane with us because it's not as massive. But that is a short-term answer. Ultimately, we want to be actually accessing these rich water resources and producing methane, which is what this middle boxes are talking about, so that we can eliminate that very large mass as well. But there's going to be some homework we have to do. And I actually think that some of the projects you all are looking at can help us essentially do that homework. And I'll talk that in a slide or two. Now, besides that, we use all the other water things. I had coffee a little while ago since I've been on an airplane. We drink water. We need humidity because every time that someone goes out and does a Mars walk, note, I don't call it a spacewalk. I call it a Mars walk because it's a different beast. When you do a Mars walk, the hatch opens and you vent, and even if you try to pump it down. And so when you vent, you're going to lose water. We're going to have accidents. I love the movie The Martian. Who here has seen the movie The Martian? I'd love to see. Yeah. Yeah, great. I love it. Actually, NASA was extremely involved with that one. And it's technically, aside from the maybe excessive number of things breaking, is extremely well done. And there will be catastrophes. When I worked in Russia, we had a fire on board the Mir space station. I never forget the day that the crew member was on board. I basically got a phone call because I was a deputy director at our office over there, and I got a phone call that said, you need to go tell the crew member's wife that there was a fire. We only talked with them for 5 minutes, and we have no idea how they're doing. And when you go through that kind of experience, you don't forget it. And so when people start talking about not having those kind of failures, I kind of get a little snarky, frankly. And because we have had them, and then actually shortly, we also had a Progress vehicle ram into it, and I'm using Russian examples, but we've lost Challenger, we lost Columbia, so we're going to have catastrophic issues at Mars too, and we need to make sure these things are robust enough. And part of one of the things that are making it robust is when you lose, let's say, a habitat, and you lose all the atmosphere in there, we got to make sure we have a way of refilling up all that humidity and all that air. And so having robust ways of producing water and oxygen are really crucial. And eventually, I don't think any of us think Mars is cool if we don't stay there for permanently, right? I mean, you're going to go to all that effort, you might as well make sure the base is permanent. And so eventually we will see agriculture fuse in as well. And agriculture is a total hog of water. Even if you're talking hydroponics, And so we are actually running numbers now to start getting a better feel for that. Even if you do it extremely efficiently, sort of next generation, it's still a lot of water. And so understanding these water needs going forward is key. But what we do know is that for any significant presence on the planet, we need lots of water. And so I think y'all are working, Sherry, with the 100 metric tons number, right?
Yep, we are.
So that is a small number. I was just at a workshop at SpaceX, and they're trying to get hundreds of people there, and that 100 metric tons is like a drop in the bucket compared to what they're talking about. And so the truth is somewhere in between, and eventually will become what they're envisioning. Of that I'm convinced. But that may take a bit. And so the bottom line is we need water. And so we're going to have to crack these issues. And this is the kind of uses that we're seeing that we need it for. Any other questions? Or we can maybe take a few questions here.
Somebody going back to the movie for a minute, Rick, The Martian, which was taken a lot off the NASA drawing boards, by the way. The wind scene at the beginning was really the only real dramatic Hollywood piece, but everything else was really very close. Do you remember at the first landing site meeting, we actually went to see The Martian? All the Martians went to see The Martian. Remember that? It just came out.
So I agree with you. Well, I had to correct one thing. I agree with you about the dust storm, which is hokey but good for drama. And the other one was hokey, was the launching off of it without any kind of action. It's made for a great story.
I think we booed during that part. I can't remember, but
let's go to the next slide.
Somebody had asked if, let's see, we were asking if you ever talked about pollinators.
I'm not sure what a pollinator is.
I don't either. So put that in the chat, whoever asked that. Christina, go ahead and elaborate on your question on that. We'll try and come back.
I love one from Mariah. It's talking about astronauts cursing. Yeah, I can assure you, they may not curse quite as much as Mark Watney, but they definitely do.
Shh, you're not supposed to say it, Mark, Rick.
Why? They're just people like all the rest of us. Okay, so the next thing is we are not dinking around. We're actually trying to figure out where that water is and close those gaps and understand exactly what it takes to produce from it, because this is totally enabling. And so one of the things which we did is at Mars, we have never combined data sets. So we have radar, we have what we call thermal data, which is where you can see hydrogen signatures on the top of the surface, and you can infer that there's water there. There's a lot of tricks we can do. And so about a year ago, we launched an effort to combine these data sets in new ways so that we can build better water maps. And so that has been a very cool effort that's underway. And we're doing it for both the subsurface ice and the hydrated minerals, because we really can't rule out either one of them. And so what you're seeing right here is we actually had two maps on each type of feedstock. And the first first team that got launched was the subsurface ice. Those two teams were so amazing and so complementary. We globbed the teams together, and we have one super team working now on this thing. And you are literally seeing some of the first results here. These are not even published right here from that study. There's actually a new variant that I literally got just today. And we'll be doing a Google Hangout showing all these things. Y'all are welcome to join us. But the first one is the blue, and the first thing shows where surface ice was detected by radar. Those are called reflections. They can actually see, they can see two reflections when they hit pure ice. They can see a reflection when they hit the ice. That's a signal bouncing back. And then when they hit the bottom, they get another reflection back that tells them that that's where the bottom of the ice. And you see this right here. As a result of this effort, we have actually filled in just with radar data where we're seeing these ice detections right here. And then the third map is not just looking at the radar, because there can be misleading cues. For example, certain types of materials could potentially be misleading if the ground's really rough and that kind of thing. And so this next map, we call it multi-data consistency. That's a really horrible name. I have a better name. But the bottom line is this is combining all these data sets to generate next generation maps. And the blue is good if you're looking for ice. Actually, orange is good too, because orange says there ain't ice there. And the negative is just as important in exploration as the positive. And as a result of this effort, you can see that we have really filled in where there's ice, and we're actually pushing those lines south. They really start to slide down to the 35 degree mark, and that is extremely exciting from a human exploration perspective. And this is just one longitudinal swath. The teams are now off generating maps, these kind of maps for the entire northern hemisphere. That's the most promising one. But then we're going to come back and do selected areas in the southern hemisphere. We don't focus as much on the southern hemisphere because it's up so high, the altitude is, that we don't get the we don't see the water there, and we also don't as much, and we also, it's harder to land because the air is so thin. So those are reasons why we're doing this initial focus on the northern hemisphere. Eventually, we need to get what's we call a synthetic aperture radar, which is really just a third radar, a new radar out there, a next generation radar, but the frequencies will be chosen specifically to eliminate that 0 to 10 meter gap so that we really can have a very good state of where that water is. The other thing which we're going to be trying to do is the junk above the water, or it's called an overburden in the community. That overburden, we really want to characterize it too, because we want to try to understand what we're drilling through. And then the other thing is we're landing on this, right? And we're building structures on it. We have got to start understanding what that stuff is. And so from a reconnaissance standpoint, that is extremely high priority for us to start using really creative people, not only in industry, but in academia as well, to start helping us come up with cool ideas so that we can really start nailing down both the water, where it starts and where it ends, and where when to start understanding the stuff that's on top of it. And oh yes, and then ultimately we have to ground truth it, because what you see from orbit, if you're in the oil and gas industry, you do not use orbital information hardly at all. You start with aerial, and then you actually will, you ultimately start sending crews there. You do core samples. There's all kinds of sounders, all those kind of things that you do. We can't do any of that, Mars. We don't have all that infrastructure to be able to go do that. And so, but we will get a chance to actually hopefully have a lander to go, hopefully to where we're thinking the human beings would be there, and actually drill down and look at what's chemically in the water, because that's crucial. And we have to look at the biology in there. And there was a question from Tommy that we should try to answer, maybe. Do you have that?
Yeah, I was looking, a lot of the pollinators they were talking about were bees.
Yeah,
So,
okay.
is it something that, is in terms of humans, we're not going to be packing all the food we're going to take with us. You're going to have to, they're looking at hydroponics and growing food. There's been a lot of experiments with closed systems and how can, you use the oxygen and things that are derived or made from plants growing and using the CO2. So I think they've tried bees up at the space station, haven't they, Rick? I'm pretty sure there's some experience at ISS.
I forget which one it was, but the point being is that growing food is crucial. Not only does it give diversity of diet, but frankly, there's two other factors that really are key. Is that human beings need, we're used to having plants around, right? So that there is a psychological piece of that should not trivial. And the other piece is that, which we are really worried about in the agency, which is that food starts to be maintained for long times, but the taste starts to degrade materially. And the problem is that, it's getting back to what we talked about in the beginning. If the food tastes crappy, that just becomes a stressor that you don't need when you're on an alien planet that with our current level of technology is basically trying to kill us, right? So we'll master it, but we do not want to be creating stressors that we don't know just because we didn't think about it. Okay, any other questions on that?
And there's a Dr. Gene Hunter, I just put it in the chat, from Cornell, has been working on space recipes for space for a long-term space flight for a long time. So you can look her up.
And I am convinced from all the work I've done with many, many crews, that is an absolutely crucial thing we're going to have to solve, particularly on these missions of 3 years or more. Okay, so the ground truthing is not only looking to chemically do it, but remember, one of the reasons we're going to Mars is to look for life. There's a lot of reasons, I would argue, but one of them is looking for life. And so most people who are thinking about that problem think that if it's there, it is close to these ice sheets. And so it might be in the ice sheets. And so we need to go pull that up. And I frankly feel like, I'm an engineer, but I spent a lot of time with science guys. I actually believe we need a control data case where we do that robotically before humans go. And that is called due diligence to protect these people that we're going to send. Okay, let's go to the next slide if we can. Next slide. There. So in the reconnaissance areas, you see the two bent circles. Water reconnaissance is really key, and it's identifying that surface ice at 0 to 10 meters. It's also really understanding these hydrated minerals and making sure we can understand depth and or density if we can ever get there. I'm not sure we can from orbital, but we're going to go try our best. And then we got a ground truth, and we got to make sure we can access this stuff relatively easily. And then eventually we're going to get what we call a special regions drill. That's just that robotic mission I talked about, where we go look and characterize the water and search for life. Now I'd like to talk a little bit about how your all's projects could factor in here, because these missions, these what I call high quality missions, are high grade missions. Let me say that because quality can be achieved in a lot of different ways. Or you're lucky to get one of them. I hope it goes to where the humans, where we think they're going to go. But when we get them, then you think of that as like having a very deep set of data, but it doesn't give you lots of data points. And in math and science, we are all taught never make conclusions based off one set of data points. And so I think that small missions can be a crucial piece for giving us a robust data set that we can use to be certain that that ice is there or that those hydrated mineral fields are there. But I would focus on the ice, because what you can do is you can imagine you land this one, and then every time we go to Mars, we drop a bunch of impactors or small landers or small orbiters, and they are all giving us different data points that we would, and there may be mid-grade quality data points, but because you have so many of them, and Robert mentioned swarm bots, which is great, you can think of it as swarming, because what we're trying to do is you're trying to develop broad knowledge that maybe doesn't go as deep, or probably won't, but it is crucial for building up a real model of what's going on there that we could actually bank on to keep people safe and alive on our next planet. The other areas that we really need to focus on, and there are small mission ramifications in every one of these, I believe, which is that we're working on Mars sample return. That's an extremely high priority. It's been a science priority. It is actually a recon priority too, because I mentioned on Apollo 17, where we had almost had a depressurization of the suit, which could have killed somebody. We need to understand the mechanical properties here. We need to understand the health hazards, and there are health hazards. I mean, the soil has, for example, perchlorates, which are toxic. We need to understand the particle distributions, so that because if the particles are the wrong size, they can function like asbestos and get stuck in your lungs. There could be exit life. All these are just problems or risks that have to be managed. And I don't mean to be creating this big honking list that says we can't do it, because we can do this. But we got to make sure we get the homework done as best we can, and these recon areas are doing it. The other two that I would mention is next generation weather. And we talked a little bit about this, but we cannot really predict weather at Mars presently. On this planet we can, but we got lots of weather stations, and we got lots of different instruments, and we can do that. We don't have that suite of instruments at Mars yet. But ultimately what we need to be able to do is predict winds aloft, and we need to be able to predict the different densities as you go up in the atmosphere. Because if you're landing, you don't want to be going and finding that the atmosphere is half as thick as you thought it was. There is a way to control that. You just bring more propellant, but it costs so much to bring that propellant from Mars that you're really shooting yourself in the foot. Really, the right answer is to understand how weather works. Just like pilots do it, like when I flew back here to DC today from Phoenix, those pilots were looking at the weather all the time. And when we send people to Mars, we're going to be doing the same daggone thing. They will park in orbit, and they'll land when they are ready to land and the weather is right. The other thing that weather does is it teaches you about microbial way, the predominant winds. Remember, I mentioned about Antarctica. where the winds flowed down it, and they put the special regions for looking for life upwind, and they are very smart. We're going to need to do the same daggone thing at Mars. I'm absolutely convinced of it. And the last thrust that we worry about on the reconnaissance side is improved communication. This is absolutely crucial. Because right now we relay everything through low Mars orbiters. We had to do that in the days when we first were starting the exploration. And there's a question from Owen about SpaceX colonization plans. I'd love to get to that in a moment. Sure. Improved comm is crucial. We're ready for what I call next generation comm, and that means we move to more like what we do on this Earth, where you've got stuff up in the equivalent of geosynchronous orbit. They can see ground all the time, and you can pump tons of data through those things. And we're going to need to do that. Like when you put a radar, the right radar at Mars, it is a data hog, and we need to be able to. And the other thing is, hopefully I gave you a sense of that there is a major role for small missions in this exploration. And what we need to do is we got to stop making sure that small missions are trying to do comm all the way back to the Earth. We got to remove that penalty and have them be able to talk with assets right at Mars and let those assets pump that data back to this home planet. Any questions on this page? And I'll try to get to the question about SpaceX.
No, go ahead and go with the one on SpaceX. Go ahead.
Okay, so frankly, I'm a Mars nut, or we actually call ourselves Martians, right? Any effort to Mars is fantastic. And so SpaceX, I've been to several of their factories. I work with them literally every week. I'm meeting with their reps tomorrow. I have total respect for what they've accomplished. They are extremely bold, and in the short run, they consistently come up short, and they'll come up with some Yahoo ideas. But frankly, any real innovator or creative force is going to come up with Yahoo ideas. And in the medium and long term, they stick it. And they do an amazing job, and they've already done some incredible things. They will get to Mars. Of that, I am absolutely convinced, and I am also convinced that that is not a competitive thing with NASA. I think that they're all part of the United States effort to explore this really cool new planet. And so I see some very exciting opportunities emerging to really accelerate Martian exploration. I don't think it'll occur as fast as SpaceX advertises, but I think it will, and it will have potentially significant impacts for your all's careers, for those of you that really want to get involved with Martian exploration. Hopefully I answered that. And I saw a comment there, didn't catch the name, but I totally agree. They will do it. NASA will do it too, as well as a lot of other countries that are already doing it. But it's going to be, going to Mars is not about one country or one space agency going. It is about a lot of entities, including companies and universities are going to do this thing, which is really exciting. Okay, let's go to the next slide if we could. Next slide. Okay, so we don't need to spend a lot of this because we've actually done this, but to do this and to get the data we need to enable that colonization, that exploration and eventually colonization, we need to go way out of the box. We need creative partnerships. So like the SpaceX thing is an example of a creative partnership, but we work with a lot. I actually head up the International Mars Exploration Working Group, 19 space agencies with companies that are doing this, and it is a totally forward-looking group, and they are already doing it. What United Arab Emirates is doing at Mars is amazing. They want to have a city on Mars or be participating in a city on Mars in 100 years, and that is one of their major space agency goals. They are as bold as the bold ones I've seen. We need to be using small missions like we talked about. And the difference is a lot of times small missions end up being just like with a STEM focus or with a tech development focus. I would love to see them tied to strategic objectives like figuring out where ice sheets are or understanding hydrated mineral fields. And I think we've grown to the point where that can be done. And you want diversity of ideas. You want university teams doing this because we don't want to get in a rut. We want to be thinking about different ways of doing it, and that you actually want that diversity so that you really get robust modeling in the end. You want to use analog missions, and there are other ways of doing this on the cheap that actually really inform how to go do this thing in a safe way. And analogs kind of amaze me because we're not doing enough of them yet. We've done some, but we really could do more. This is where you go out and do like a simulated one, like that picture down the bottom, which is probably up in Antarctica maybe. But the point is, you can learn a lot. Amundsen, before he made their first successful run to the South Pole, the first one ever for human beings, they actually lived with Indian tribes. They understood how you use dogs and how you do all of those things. And we need to be trying to do similar types of analogs to really understand how we go execute Mars. Let's go to the next slide. Yeah, Mars dogs. I love that, Michael. It'd be nice if they wouldn't do so hot in the thin atmosphere, but we'll probably come up with the equivalent of that, but it'll probably be robots. Okay, next. Okay, so this slide I really love because, frankly, I think we started this off, and I told you I had a bunch of starts, different starts. Like I did the history degree before I started doing aerospace engineering, and I will tell you that when I was in school, my biggest worry was finishing on time, right? And in retrospect, I would say I was dead wrong, but part of growing is realizing you're dead wrong sometimes. And so one of the biggest things you can do is, and I know Sherry's an enormous advocate of this, interning, co-oping, whatever you want to say, is a massive way of learning and making money. And even if it means delaying your graduation date, if you were a co-op student for NASA, you make, I think, a GS7 as an undergrad, and that is a significant pay that you can actually do it. So even though you might graduate a year later, I had to graduate a year later. You know what? I will tell you personally that I was training astronauts literally within 2 months of being there, and they want you to learn, they want you to be happy, and they want you to find the thing that totally jazzes you. And so they just know, and NASA's is not alone. There are tons of companies like that. And so just realize that that's an incredible opportunity, even if it slows you down a little bit. But in the end, if you find something you love, do you really care? Sherry, anything you want to add to that?
No, we've talked about internships. We'll be talking more about internships. A lot of them have applied for internships, and we've been pushing that message a lot, Rick. Thanks for reinforcing
No, that's great.
it.
And the other thing I would say is that if you can afford it, if you find an area that you totally love, consider a unpaid internship as well as a way of getting your foot in the door. Now, there's a cost with that, right? But if you're creative, you can often find ways of doing it. And sometimes there are indirect ways of getting it partially funded so you can do it. And the reason I stress this is that in the Mars area, for example, it is so new. It is like the internet was 25 years ago. You can actually be amazed at how much you can contribute, but figuring out your niche, where you want to be, is hard. And so if you could find an area that you totally rock for you, that you love, but the only way to get your foot in the door is with a volunteer thing, that can be a very powerful tool for getting your foot in the door. I have a guy that works for me now. His name's Max Parks, and he came in as an unpaid volunteer or an intern. And you know what? Max would go sit with the scientists that are managing every single major Martian program. They all have lunch together. Max would just sit with them, and you know what? He found a job at Goddard Space Flight Center that is now paid. We are paying him because he rocks so much, and that is incredible that he's actually done. He will have a totally cool career, and he's now applying to grad school and that kind of thing. But he's foot's in the door, and he had to just find his space. And I want to talk a little bit about figuring out where you put the foot, right? And so obviously Googling things is great, but I will tell you that when I went back from the first time I was at NASA headquarters back to the Johnson Space Center, and then wanted to go back into doing stuff Mars full time, I literally decided I wanted to figure out who was doing anything with Mars, and I literally would call people up and say, can I come talk with you for 45 minutes about your work? I never asked for an hour, because if I asked for an hour, they would all think, oh my God, it's too much. We're not doing this. But if you ask for 45 minutes, they end up giving you an hour and a half. And so the point I want to try to make is if you see people that are doing stuff you think is cool, you can, if you can go visit them, that's best. But if you can't, don't do it. Don't do it and get off the texting. Call them, and even better yet, use FaceTime or whatever so that you can actually see them eye to eye. And then, because you're going to see when they don't understand what you're saying, it just allows you to get a lot more information out of that conversation. And do your homework. Because I actually would Google them, and I would research what they were doing and try to have everything, and I would have my at least initial questions, things. So I didn't sit there, kind of twiddling my thumbs because I hadn't thought it out. And the last question you should absolutely ask is, who else should I talk to? Based off of your conversation with them. Always put that one in there. And you will be surprised at what you learn. And I will tell you this, I felt like an idiot sometimes doing that because I was just calling people out of the blue. But you know what? I would say a full 70% of the people I met, I work with on a day-to-day, not on a regular basis, doing my job right now. And I am so thankful I did that. It is not even funny. There's some other ways here, but the bottom line is we all only get to live one time. And so if this is the kind of stuff that really excites you, do not take no for an answer. And you will have multiple false starts. NASA has a fellowship program that because I worked there, I had to apply 5 times, but I finally got it. And when I got it, it was like perfect, because if I'd gotten it earlier, I wouldn't have even been researching with the right people. And I totally love the work I did. And so even though I didn't get it when I thought I'd get it, it worked out totally cool.
So we're getting close. We're at 2 minutes over, Rick. So you want to get to the last slide?
Yeah, last slide if we can, then we'll just talk about. So we have a website, we do Google Hangouts and all that, and we strongly welcome, if you have an interest in this work, and obviously if you're in this class, you do, we welcome you to visit our website. We have a Twitter, and we try to pump out information on that Red Planet Rick Twitter account as well. And again, do that research, and if you can't figure it out, send us a note. Because we strongly believe that Mars is doable, but we need the kind of ideas that you all will bring to the table. And the last comment I would make is, do not underestimate your ability to contribute. And I want to talk just briefly, and then I'll let you go. You guys are used to working with people across the planet better than someone might be at Sherry's in my generation on average. You all are more IT savvy. The computer systems going out to Mars, they ain't going to be like what we have on our iPhones. They're going to be incredibly self-reasoning systems so that we can essentially put a mission control center in a box. And we need people who are thinking out of the box and who are used to computers doing it. You all do that all the time. I mean, I would even argue that kids that are in school today are in a much more inclusive environment, and Mars is going to happen because this whole planet pushes out in that direction, which means you don't exclude people. And so you need to make sure you're pulling in all of those ideas in a very collaborative way. And if we get all that kind of energy going there, not only can you make a contribution, but we'll actually crack the nut of how to set up shop on our second planet. Any questions I can try to answer?
Well, I think we're getting amazing stuff in the chat, Rick. You're seeing it go by. I had another one I saw. This is the best talk ever. So you're already up there in the ratings in terms of what you've delivered tonight. We are going to be posting Rick's talk. He's given us the permission to do that. It will have the Google Hangout slide and other things that you've been looking for. I've posted some resources like the YouTube to all the human landing site mission meetings that we've had in the past, all the presentations. So that's as a resource. And we will be putting that resource also and posting that on the forums. So we want to make sure the mission document with the constraints, I'm finishing that up tonight, and we'll be posting that, and you already have the PDR posted as well. So again, we're going to be we're actually going to be working towards getting Rick some concepts on how we're going to test that water feedstock on the planet, getting ready for human exploration. That's going to be your job. So all the background you got tonight, I felt, and we felt it was going to be something that would be not only the big picture and the future picture and not that far away, but also something that's going to be needed by NASA in terms of understanding what that water ice is like, right, Rick?
Yes, actually, and if I could digress for one moment, there was a great question by Lakita about having nurses on our teams. What I would say is that when humans move to their second planet, everything we do on this planet, we are going to do on that planet.
Yeah.
So you will have doctors, you will have nurses, you will have engineers, you will have biologists, they'll be called astrobiologists, they might be called astrodoctors, whatever. They'll be different in that regard, but they will set all those disciplines, including stores and including all those things. The things we do every day in our lives are going to be on that planet too at some point.
Can you
And
imagine?
so,
Yeah, go
for
ahead.
good and for bad, right?
Yeah.
But that's what human beings are. And I would just say that just realize that there are a lot of avenues for doing it, and realize that right now, it is like the internet 25 years ago. Your capacity to become involved, and Sherry will scream at me for saying it, but the internet 25 years ago, you did not even need a college degree if you were willing to dive in and learn. It was so new. And it was so dynamic, and it required people who were willing to wade in. Mars is like that right now. I am not advocating not having a college degree. I've had to agonize through 3 of them, and I'm very thankful for having done it. But you can make contributions in this area maybe a lot faster than you can in many others right now because of the newness.
And that's part of the space we're pushing you into in terms of the mission concepts, as Rick talked about before. These are entry points, and I've had this validated by Rick, by other people at NASA headquarters, and other people in the Mars Exploration Group, and other missions besides Mars. This small package, small mission concept is going to be an emerging mission line within NASA. In your career pathway, which is not very far from the workforce, this is going to give you more traction in getting involved in things, easier to get involved in small missions like this than some of the much larger ones that are highly competitive. So we're giving you practice in this for a reason. And the mission concept that you're going to be working on with your teams and your mission PDR document you're going to be forming up is going to be really good ways for you to kind of explore what these small missions might look like.
Sherry, can I just address one other question?
Sure, go right ahead. We're in the after show by now, just so you guys know.
Yeah, so Elizabeth asked a question about could further space exploration, colonization, other planets bring unity to the Earth nation? I love that question. And let me give you 2 things. I worked space station for 12-ish, no, probably more than that. And I will tell you that when we lost the Columbia orbiter, that was extremely devastating at NASA, because in Johnson Space Center, those were close friends. And when we lost them, you can imagine. And I will tell you, the first people I heard from were not the people I expected from. They were from Russian counterparts who have lost crews as well. And they were calling us, and their only message was, how can we help? And despite the fact that the United States and Russia, for example, have some significant differences right now, every day we are in space with Russians, Europeans, and Japanese, and Canadians at different times. And we are working together, and they just don't have, their lives are on the line together, and that forces a bonding that is incredible and an understanding that is incredible. And Elizabeth's question completely nails this thing, because when we go to Mars, it is going to be an international missions they're going to go. And the bonding thing, can you imagine what it'll be like when that first crew touches down on our second planet for the first time, and out come people from all over this planet? That is totally amazing. And the bond, what that does for transforming our perceptions of ourselves and our relationships with others, I think is a major reason why we go do this. It's not the only reason, but it is a very significant reason. So Elizabeth, thanks for the great question.
Well, you've got Rick for, I don't know how, it's getting 9 o'clock there on the East Coast there, Rick.
I can take a few more, just 2 more questions, or 2 or 3 more, and then I should probably get going. But thanks, it's really fun.
So I'll let you pick, you see the questions.
So there's one about radiation. Let me try to address that one. That's a great question because people worry about it all the time. The problem on going to Mars is not at Mars. I mean, it is a problem, but basically with the Martian atmosphere, when you're in a habitat, when there are some really cool ideas about habitat design. So if your radiation damage is actually an aggregate of your total exposure, that's what you really worry. You can have acute radiation, that's also a problem, but in general in space travel, the big thing is just your constant damage by radiation. And so as long as you sleep, maybe underground, you don't want to be underground all the time. How boring. You go to another planet and never see it. Look outside the window, right? So, but if you sleep, where it's underground and you're protected and you have an atmosphere at Mars, that's it's essentially like being on the space station, and we know how to manage that level probably at least for 6-month missions. And I think we can easily get there. The real trick is the outbound and inbound legs, because you're in deep space. And in deep space, we have to be, we're going to have to make sure we really understand it, but we're measuring those radiation levels. We are understanding that damage there. And really, the docs and researchers that study this, they're not worried about that being like killing a person on the way back, but we have to learn how to mitigate the cancer risks when they get back. And they are doing some really fascinating research into drugs that actually will mitigate radiation cancer damage risks, for example.
Well, I was at JSC too, part of the Mars Odyssey team. We had a radiation specialist, and he was talking about how they're creating new fabrics for the surface suits, basically, that will be more radiation resistant. And so
there's a lot of
different kinds of
things. A lot of different ideas, and we're going to need to look at them. I mean, it's not I considered a showstopper right now in terms of sending people there. We have bigger problems. So, for example, think of it this way. The psychological piece, I don't think we can even totally understand because we haven't attempted it. But I think with enough thought, we can make it, we'll figure it out and we'll learn along the way. One of the big problems is that if you have an emergency medical situation on the space station, we can get them down to Earth really fast. I'm talking like within hours, and so you can take care of it that way. On Mars, you're gone. And so we're going to have to either have several doctors or have a nurse and a doctor or have someone who's trained up to do things, but they can't just be trained up to do the really easy stuff. They may have to do a root canal. And we don't worry about that on the space station. But over a 3-year period, you could develop a major dental issue that is a big deal that requires surgery. And we got to make sure we can handle that. So the range of things that we worry about will increase, but we'll figure those things out collectively of that.
Yeah. All right.
We'll take one more question and we'll try to go from there. You pick one.
I was going back. Kevin's asked this about 3 times, and I'm trying to go back. It had to do.
Thank you, Kevin, for the question.
He was working on. It was something. Oh, here it is. Okay. Does different atmosphere? I don't know if you have this in your.
Say that question because Tommy just asked one I totally love.
Okay, go ahead. I'll say this one.
After Mars, and I would tell you this: human beings, our knowledge is expanding at exponential rates right now. Mars is just the place that we're kind of lucky. It's like the only other planet that we can actually live on with our current technology right now. So you don't have to decide between multiple planets. You got just one. This is the bottom line. And that's very cool. And there's a lot we need to research on it, not just because it's cool, but because it teaches us about this planet, which is totally cool. But eventually human beings will go out to other places. They may not be able to land on them because some of them are pretty daggone hostile, at least with our current technology. But eventually human beings will keep pressing out and exploring into this infinite cosmos. And our understanding of ourselves and of our role in society and what we're really capable of doing and what we have to worry about ourselves doing. You have to do both, right? Is going to expand so much that it's really incredible to think about. It's very difficult for finite human beings, but they're just at the beginning of exploring past the womb of their planet, their home planet, to understand what really is possible as you go further out there. And I think it's totally exciting. And you guys are going to see it front and center.
Well, and what, I mean, again, you talked about our generation, Rick, what they have to look forward to in the kinds of things and with the technology and the far reach we have to actually use this whole fleet of things going across our solar system and beyond, you're going to see things in your lifetime that we could have never imagined.
Yeah.
And I mean, we were old enough to see Neil Armstrong climb down the ladder and actually put those feet on the moon, where you're going to see the first footprints on the next planet.
Yeah.
So it, just from our recognition of just that little place, 250,000 miles above us, you're going to see something that's going to be, 1,100-day trip that is unimaginable in terms of having that stake of humanity going to the next place.
Yeah, and you had the last question too.
You want Kevin's question?
Absolutely.
All right.
We're going for stump for the chump.
Yeah, here it is. See if you can bag this one, Rick. Does the different atmosphere on Mars affect chemical reactions to synthesize water as well as things such as curing process of hardening cement? So like in trying to put together habitats or infrastructure, is there going to be a problem being that the atmosphere may react differently or whatever? I think is what he's asking.
So the atmosphere at Mars is largely carbon dioxide. That's actually not very reactive. I mean, and so the good news, and it actually has a resource we totally need, which is oxygen. And so initially, I would say that atmosphere it's actually a good thing. We can get the oxygen out of there, and that's probably that's probably the first use of natural resources at Mars will be that. It is thin, and that's probably the first challenge of it. In the sense that that it's hard to land there, but we can make that work, and because it's thin, you get radiation. Because it's thin, it's hard to work out there. But we'll probably have work tents where you go out there and they're partially pressurized, because working in a Mars suit, which will hopefully be the current space suits are about 350 pounds. I mean, when you put the gloves are like having your fingers in a balloon. And in earlier glove things, the gloves would actually pull fingernails off sometimes. They were so difficult to use. And so we don't want that on Mars, where you're hopefully going out on Mars walks every day or every other day. And so we're going to need some radical new designs on spacesuits, and we've got some really cool and creative ideas starting to come into play. But ultimately, that atmosphere is kind of nice, because if you can actually envision having essentially like a tent that's enclosed where you pump up the pressure with the atmosphere. It's carbon dioxide, which we can't breathe, but if we can get the pressure up there, you could walk in there with just a lightweight oxygen mask and do work, and on machines that you don't want to necessarily bring into the habitat because they've got dust. And so it's like having a garage at Mars, really, if you think about it, except it's a slightly more complicated one. But the point is that you can go work on your rover or whatever you're using, or your dozer or whatever it is, and work on it where you're not bringing in a ton of dust into where the people are being there. And that atmosphere will be key for allowing us to do that, because we can just operate in a CO2 environment.
Well, and a little bit more on the cement and all that. I know that Doug Ming out of Johnson Space Center, Ellen Stofan, who runs the science side at Johnson as well, have been working on looking at 3D printing on Mars, and what assets do we have on resources on the planet that can we use those resources, that iron rich rock and things, to actually print things without having to bring the stock with us.
So I was at a meeting this week where we are looking at 3D. One of the things we looked at, we were talking about how you use resources to 3D print, I will tell you, I completely underestimated the potential of that technology about 5 years ago, but I realized how wrong I was. And the bottom line is that's going to be a massive tool set. And the other thing that's massive is that if you have to bring spare parts for everything that could break, it makes Mars missions very expensive. If you can 3D print them from a generic stock and you don't have to bring the generic feedstock there, that is transforming.
Well, and we've had the mineral camera around Mars since 2002 on the Mars Odyssey, and then there's the Mars Reconnaissance Orbiter has CRISM and other higher res type of mineral maps too. And so knowing what's in that exploration zone, knowing what assets you may have besides the water stock to draw upon, and then also the really interesting science, is going to be a really important thing in terms of having those assets close.
Yeah, exactly. So anyway, I guess I should probably let everyone go. And I just want a couple things I want to say is that don't never take no for an answer, because this stuff is too cool.
Yeah.
And if you're interested in this stuff, go after it with a vengeance. And actually, you'd be surprised. Anyone who's doing this kind of work wants you to find your niche.
Yeah.
And Sherry, I think will testify to that.
Oh,
You know,
absolutely.
we do have the Twitter thing, and that's a one way to learn, but there are lots of other ways to learn. And we do the Hangouts, and we strongly welcome your participation and involvement in those, because frankly, we need ideas, and you'd be surprised what you can do. So thank you all for the time.
Thank you for marathoning it, jumping on a plane, flying all the way across the coast, and getting on with us tonight. So
No, it's great. Thank y'all. Take care.
I owe
Bye-bye.
you next time I see you, Rick. Okay.
See ya.
See ya. Bye. All right. So I think we're going to call it a wrap tonight too. And we're excited that Rick allowed us to, come in and intersect into the stuff they're planning for. And they've been very active getting these landing sites up and running. So you all are going to have the job of actually characterizing those landing sites. You're going to pick a landing site. We're sending you the information and the map that he showed. I think it was 47 sites I think we've got right now. And you're going to pick a site, and you're going to give us a concept that's actually going to characterize that ice. And the mission document will give you the kilogram constraints in terms of, we're actually giving you your mission concept, and I'm looking at it right now. It's going to have the constraint of 5 kilograms. This is a small package we're going to put on the surface. You're actually going to be pitched off from an orbiting spacecraft that's about 250 kilometers above the surface. And you're going to be doing an intra-descent landing. I've been working with Rob Manning over at JPL on getting things down on Mars. He's the world's expert in landing all the rovers and everything else we brought down. And it was funny because I asked Rob, tell me what you think. This is the size I'm thinking of. And what do you think it would take to get it down? What size, heat shield? And he sends me the most amazing email. It's just like, well, here's what it is. And yeah, it costs about this much or whatever. No, he sends me this whole thing of an email with all these calculations. This is what I think it'll do. This is the angle of attack, blah, blah, blah. It was just hilarious. It's like, Rob, it was just an email. But no, he gives me the whole thing. So we're getting the information from the experts. You're going to be putting that design concept into place. You're going to be looking at trying to measure with that 5 kilogram package. You're going to be looking at the depth of the ice, the type of ice, the temperature profile. Maybe there's impurities that we need to know about. All kinds of things that you're going to choose from. We're not going to tell you what to do. That was just the start of a menu. You're going to tell us what humans are going to need to know about that ice. And the main thing is that Rick and I have talked about is this is why a robotic precursor mission has to go down and actually say the ice is there and characterize it. And we want many data points. So we're going to give you extra points if you want to be able to multiply this probe into a bunch of probes, and you pitch it off into like a landing field and you get data points from different places. That's going to actually help us understand, and that's kind of our concept as well, in terms of getting multiple data points from a single site to say this is about where we're finding ice. Oh, we got this far on our landing probe and we didn't find any. So if you can get subsurface to know how deep the ice is, do you have to go through several meters, of regolith, which we call the dirt on Mars regolith? Is it right just barely into the surface? We need to know those kinds of things to know how we're going to actually get that resource to use in terms of the human landing site mission. So there's going to be different types of, it's not a real dense document. The communication package we're going to provide in terms of the main communication between the orbiter and your different mission concept. You will have about a 0.025 kilogram that you're going to have a small communicating device that can then talk to the local device that's not going to be very far away from you, that'll radiate the commands and data acquisition up to the land or to the orbiter. So all these things will be in a document that we're going to post. And then your teams are going to get together. We've given you a very complete preliminary design review outline. I want you, the main thing, and we're going to reiterate this in all of our communication, follow the outline. Use the same numbers. We just got done talking to people that are proposing to NASA right now, and some of the, and I've been on NASA reviews as well. If you don't follow the outline, we can't follow and assess what it is you're doing. We can't give you feedback. We need to be able to use the same things and know what you're talking about. If you don't know what some of the sections are, communicate with us and we'll make sure that we put that and post that to you. We don't want anybody to have any idea that that's jargon they don't understand or what it is. We will make that happen to make sure that you understand.
We've got a
And-
couple other things to support you for your
Sure.
PDR as well, in terms of meeting with your project managers and the deputies. We'll be scheduling a meeting with you very soon, as well as checking in about halfway into the session or into the project, right, Sherry?
Yeah, we will. And you're going to actually post include the after show with Rick on it, right?
Yes.
Okay, that's great. So, yeah, so you need to, I would follow all the labels. Jesse, I'm looking at your question. Do we need to label exactly 1.1.1? You need to do exactly those sections with your description or your, information under each of those subsections. We're giving you NASA protocols. We're giving you the view of, especially, like I said, I've been a reviewer, and what reviewers would need, you need to make sure that you're following it the same outline. If something doesn't apply, you can just have that outline header and just say, does not apply. And you can just go on to the next one. Okay. It's been pretty amazing. I'm trying to think, I think you have them over in your office, don't you, Dan?
What is that?
Oh no, I do here. So we might even post, we're going to ask from the last section of LaSpace. We had some preliminary design reviews that were turned into us, from all the teams. And we had some that were absolutely stunning from teams that, the detail and everything else that they provided in these documents was amazing. We actually took some of these to the huge AGU meeting that's the biggest science and Earth and space science meeting in the world, to Washington, D.C. this last December. And we took some of these from the last LaSpace, and we were showing them to the NASA mission formulation people, and from NASA headquarters right in DC. All those people were there. We were right next to the NASA booth, and they were looking through these documents and saying, these are undergrads? And they were amazed they said, this looks like a step 1 proposal to a discovery mission that the professionals would turn in. So we want to give you some ideas of what exemplary looks like. We'll probably, let's talk to the teams that we have here, the 3 teams that we can maybe share with you all to say, here's what an over-the-top type of PDR looks like, and give you something to shoot for. We're not saying everybody needs to do this level, but it would give you an idea. The top 2 teams were from Puerto Rico. We just heard from some of them the other day. They just went 3 days without water and power. And they're still doing this kind of work. So the communication in your team, the way that you can kind of sort out tasks, meet asynchronously, don't worry about having to all be face-to-face at the same time. Make a contract of how you want to treat each other and how you're going to communicate. That's something we talked with our evaluators today about. How can you as a team do a local coming together about, here's how we're going to make this work, and here's how we're going to be inclusive. We know we're not all together. We're not co-located. We're all over the place, just like NASA is when we have our team meetings. But we want to help you be successful in learning how to really optimize that time with the team and be able to get those things out. So anyway, I'm reading the comments.
Yeah.
I just looked twice because all of a sudden Dan's on Mars. Wait a minute.
I had to
You're
test out
freaking me out,
that.
Dad.
I had to
You're
test out
freaking me
that new
out.
feature.
It's time to go home.
It is.
But anyway, yeah, Delene, Puerto Rico. We had everybody from MIT to everything in you can imagine. Puerto Rico nailed it. It was amazing. And so again, this is not about where you're from. It's about how we can help you approach and be thinking in terms of a professional. That's what we want to help you do.
And we have
So-
the belief and
Yeah.
the expectations that all of you can do that. I mean, we are here to support you. Our goal is that you walk away from this experience not just even better prepared, but those documents that Sherry showed a while ago. I mean, those are going to be your tickets into. I would
yeah.
suggest your next interviews that you go to, you take this and show, look, this is what I was a part of with NASA.
This is part of what my team or what our team
Yeah.
did.
This is what I did, and this is what I know.
That's a real game changer. So anyway, we ought to get off and let you all go home too, but we want to just get you geared up and thinking about you know, how you might imagine and dig in and kind of unpack that. This is a real project. This isn't a fantasy project. They need to do this. When we had our last project, which was not exact, it was not like this. It was on Mars last time, but the head Mars scientist at NASA headquarters, when I told him what we were doing, he says, "Can I see their concepts? I'd really like to see what they have in mind." You know, and it's like Rick says, you all are on the cusp of being able to do something really amazing because we don't know how to do this yet. So we're looking forward to seeing you and seeing what you can do. We're here for you. We're your assets. We're your consultants, we're your mentors. You can use other mentors as well if you have local sources, but if you don't, we're here. Okay, so with that, I think challenge accepted. Yes, Esteban, good for you. We're ready to go shoulder to shoulder with you too. So this is an amazing thing. We're excited, and we will be looking forward to working with you for the next few weeks. Okay. So with that, I think we just say goodnight.
We say goodnight.
All right.
Good night, everyone.
Y'all have a good week. We'll see you back next week, and hopefully we'll be talking to you in between. Good night.
Hi, everyone.
Good night, everybody.
Yeah, you're all on
Good
Zoom.
night.
Good night.
Hello. Even though like you're right here.
Just a chance to say goodnight.
No chat necessary.
The message doesn't even go in. Don't.
Good night, everyone.
Good night.
Good night.
Team 42.
Team 42.
Team 3.
250.
Pull out your team. That's right.
Shout outs.